Hello, everyone. Today we'll be talking about Reinforcement Learning 104, which is titled Scaling RL from PPO to Real-World Agents. Previously, we have been 纸上谈兵, talking about RL on paper, and today we will throw away the paper and look at real systems, especially how RL connects to modern RAI, such as LLMs. And today, we'll move from theory to systems. This is where RL becomes powerful and complicated. Last week, we saw how Actor-Critic leads to PPO and why PPO dominates modern RL. But here's the real question. How can we really make this work on a real system? And the key idea is that PPO works in theory, but the reality is very different. And real systems introduce new challenges we didn't see before. And we need to go from clean algorithms to messy reality. The problem, again, so far, PPO looks beautiful on paper. However, deploying it is a completely different story. IR works, but scaling is very hard. Real systems introduce noise, constraints, and also scaling problems. For beginners, the intuition is quite simple. Learning is slow, and training can be unstable. For practical problems, we have sample inefficiency, meaning that we need lots of data for our algorithm to converge, as well as engineering complexity when implementing these algorithms. And finally, for researchers, there are too many challenges, such as real-world deployment, as well as system-level constraints. And the idea is that a good algorithm is often not enough. So what's missing? Before we can actually cook PPO on a real system and a real GPU, we need a bunch of different things, such as scalable training, stable updates, constraint handling, as well as system design. And this is where modern RL begins, and algorithm alone are not enough. Le cartel. Today's journey will have three main courses. First, the PPO. We'll look at some math, but worth it. And PPO will give us stable updates. The second phase, we'll talk about CISPO, which improves how we use data by preserving learning signal and basically better updates via important sampling. And finally, we'll look at the Forge agent, which is Minimax LLM from the company Minimax. And here we'll go from algorithms to real systems. And the important idea is that CISPO is not about constraints, it's about better learning signals. And we'll go from stability to better signal to real systems. First, let's quickly refresh PPO. It is an actor-critic algorithm, meaning that we are working on the policy gradient methods. However, we also add clipping methods, which means policy plus value network, and we limit how much the policy changes. The second ingredient is stable updates. Here, we only have small, safe improvements, and we avoid breaking learning. And finally, this is an on-policy method, meaning that we learn from current policy data, and it requires fresh rules. These three components are why PPO became the default baseline a few years ago. And PPO is basically the stable actor-critic in practice. Let us look at some intuition before looking at the math. Too big a change can break learning. And PPO is very simple. For beginners, basically, we don't want to change the policy too much at each step, and small safe improvements are warranted. For engineering mechanism, basically, we'll modify the loss function, as we'll see in the next slide, and we add a term that limits policy updates. For researchers, we give this to be two terms, such as clipped gradient objective or constrained policy updates, and we basically update, but do not overreact. And now let's look at the formula. Initially, it may look complicated, but the idea is quite simple. We first compute an update, and then we clip it to make sure that it doesn't change too much. The first idea is the policy ratio. We call this the surrogate objective. Essentially, it's a ratio of new to old action probabilities, where pi theta denotes the new policy network, and pi theta old denotes the old copy. Basically, the loss function consists of maximizing this term, where this term is a minimization operator, where the first argument is r theta times AT. This is just like the policy gradient. We want to maximize actions with a positive advantage. However, we wish to clip the r theta between 1 minus epsilon and 1 plus epsilon. And for practical reasons, we typically select epsilon to be 0.2. So the ratio will be clipped between 0.8 and also 1.2. And this will limit how much policy changes, and it does not allow large jumps. And basically, we'll compare original update versus clipped update, and we'll take the safer one. And finally, for academias, we call this constraint policy optimization or approximate trust region method. And so safe improvements over aggressive updates. Now, let's look at the problem of applying RL for LLMs. What are we even optimizing? LLMs are simple. They are just policies over tokens. LLMs generate text by predicting the next token. For beginners, it's quite simple. We predict the next word or next token, and one token at a time. And for engineers, we implement this as an auto-regressive policy. Basically, we take in the query vector and all of the tokens that we output prior to time step t, and the policy basically decides what is the next token. And for researchers, IR basically operates at token level gradients, and training is a sequence of decisions. Basically, it's an optimizing sequence of token probabilities, and we call this auto-regressive token level optimization. So what are some problems of PPO in LLMs? Basically, let us look at the policy ratio again. It is the new to old action probabilities. So let's say pi theta is very large compared to pi old. In this case, RT theta will be quite large, and we'll clip them to be, say, between 0.8 and 1.2. And we'll compare this to the RT theta AT, and very likely we'll take the clip path, which means that PPO clipping can drop token contributions in long reasoning tasks. And the key idea is that PPO may ignore exactly the tokens we need, and some important words are rare. And for engineers, large ratio RT can get clipped, and important updates will be removed. And for researchers, this means that token gradients get zeroed out and learning signal is lost. So here, because we're taking a cumulative sum of the whole sequence that we are talking about. So how can we fix this problem? The answer is CISPO. And the key idea is that instead of ignoring tokens, we'll shrink their impact. And CISPO clips importance weights, preserving all the token updates. Here, for beginners, we'll keep all the tokens and we'll reduce extreme updates. For engineering, for implementation, we'll simply clip the ratio RT, which is just clip. And the RIT theta is just similar to in PPO. Basically, we have the new policy of outputting the next token versus the old policy of outputting the next token. It's just the ratio of two probabilities. And the loss function, basically, we want to maximize this term. A is our advantage. Log pi theta is basically we have in the policy gradient, and we let's compute the probability of output in the next token, given the query tokens and also the previous tokens. And stop gradient RIT theta basically will clip the important sampling weights instead of the whole objective. And in this case, we'll be able to preserve all the gradients. And stop gradients means we'll do a forward pass without doing a back propagation. And now, why CISPO works for LLMs? So we know that better signal will lead to better reasoning. And some tokens are rare but critical. For beginners, words like wait, actually, let's check, these tokens trigger better reasoning. And for engineers, PPO suppresses these tokens, CISPO keeps them. And for researchers, this actually preserves low probability, high impact tokens and improves reasoning plus convergence. And so low probabilities gets to preserved, and these are important for reasoning. And the smartest tokens are often the rare ones. So now, what is the key idea behind CISPO? So let us look at the following simple diagram. The x-axis, let's say, is the RT, the policy ratio. So we have 1 plus epsilon and 1 minus epsilon. And for y-axis, let us say this is the gradient contribution. And positive means active gradient contribution. And negative axis means flat contribution. And in the middle, learning happens normally when the ratio is between 1 minus epsilon and 1 minus epsilon. However, outside of it, PPO will flatten the gradient, which means no learning. And so what if we don't want to drop these tokens? And this is exactly what CISPO fixes. So from previous slide, we know that the middle region, which is a safe zone, so RT is between 1 minus epsilon and also 1 plus epsilon. And outside region, which is the danger zone, this is the clipped region, and the gradient will become flat. And no matter how important the token is, PPO stops increasing, decreasing it. And basically, there will be no learning. So for example, important tokens such as weight, this will be rare in all the policy, and it may suddenly become important during the training, and you will generate a high reward, and your R ratio will be much greater than 1. And PPO will clip the update, and gradient will be approximately constant, and meaning that learning signal will disappear. So PPO doesn't trust extreme updates, so it stops learning from them. Now we can look at the IL and scale, which means that more than algorithms. Training real agents is not just about PPO or CISPO. To scale IL, there are a number of parameters such as system throughput, like how much tokens you can process per second, as well as sample efficiency, and also stability as well. And IL performance typically is a product of these two terms, systems times algorithm. For beginners, IL typically needs lots of data to converge. For engineers, this depends on many parameters such as rollout, training, as well as input-output bottlenecks. And finally, for researchers, we optimize training yield as the product of throughput as also as efficiency. And Forge, we can look at this. This is a agent-native IL framework developed by the company called Minimax. And it's an agent-native system when they are trained on real agents in real environments. And they train agents, not just policies, and they support arbitrary agent scaffolds. For beginners, IR has to happen in real tasks instead of just toy environments. For engineers, this supports arbitrary agent setups as well as standardized interaction interface. And for researchers, this is called generalization across agent scaffolds. One of the novelties is that they decouple agent from training. First, basically, they separate agent from the RL engine. Agent is basically a black box, and training is independent. And for beginners, this means that we can plug any agent into system engineering. We implement this as a decoupled architecture as well as standardized interface. For researchers, this improves generalization across environments, meaning that we don't want to overfit to one agent. Now, how Forge scales RL? Basically, scaling requires system innovations, and 3 of them are as follows, such as asynchronous scheduling, tree structure sample merging, as well as massive parallel rows. Basically, this means that we run many experiments at once, and we need to balance throughput versus our policy data. And according to the webpage, they claim this has a 40 plus training speed up, meaning that smart systems leads to faster learning. And I have extracted a paragraph from the webpage. Basically, they say that throughout the construction of Minimax M2.5, our IL systems navigated over 100,000 distinct real-world agent scaffolds and environments operating with context lengths of up to 200,000. The system maintained a daily processing throughput on scale of millions of samples, realizing consistent reward convergence and genuine capability improvements in the underlying model. Integrated with our CISPO algorithm and composite reward framework, M2.5 pushes the frontier for efficient and reliable real-world productivity, achieving our mission intelligence with everyone. So now let's wrap up this discussion. So the key takeaways are as follows. Main progression, we go from PPO, which is stable updates, and then we go to CISPO, which have better learning signal, and we move on to Forge, which is scalable IL systems. And the future IL is just systems, not just algorithms. Basically, algorithms times system times your data, and it's no longer just algorithms. And want to go deeper, as a complementary resource to the full session recordings, you can visit my YouTube channel as well as my Bilibili channel. And this is the structured versions of my lecture content, and they are easier to visit and review than the 1-hour recording on the Notion page. And for now, I have IL 101, 102, and 103 available, and more will come soon. And you can learn at your own pace. And this is the end of the lecture RL 104. Thanks for listening.